Electric current is the flow of electric charge through a conductor. This fundamental concept forms the basis of all electrical circuits and devices we use every day. Electric current is measured in units called amperes, abbreviated as A. 1 ampere represents the flow of 1 coulomb of charge per second through a conductor. To visualize electric current, imagine electrons moving through a wire like water flowing through a pipe. The electrons carry electrical energy from one point to another. Now let's explore how components can be connected in electrical circuits. There are two fundamental ways to connect components: in series and in parallel. In a series circuit, components are connected one after another in a single path. This means the current has only one route to follow through all components. In this series circuit, we can see that current flows from the positive terminal of the battery through each resistor in sequence and returns to the negative terminal. The current value remains constant throughout the entire circuit. Now let's examine parallel circuits, which work very differently from series circuits. In a parallel circuit, components are connected along multiple paths. This creates several routes for current to flow, and the current divides between these different branches. Here we can see how current divides in a parallel circuit. The total current from the battery splits into 3 separate currents, each flowing through a different resistor branch. An important principle in parallel circuits is current conservation. The total current entering a parallel junction must equal the total current leaving that junction. This is known as Kirchhoff's current law, and it ensures that charge is conserved in the circuit. Finally, let's briefly discuss voltage behavior in these two types of circuits. Voltage drop refers to the reduction in electrical potential as current flows through circuit components. The behavior of voltage drops differs significantly between series and parallel circuits. In parallel circuits, the voltage is the same across all branches. Each component in a parallel branch experiences the full source voltage. Understanding these fundamental concepts of current flow and voltage behavior in series and parallel circuits provides the foundation for analyzing more complex electrical systems and applying Ohm's law in circuit calculations. Ohm's law is one of the most fundamental principles in electrical engineering. It describes the relationship between voltage, current, and resistance in electrical circuits. Let's break down each variable in this equation. V represents voltage measured in volts. I represents current measured in amperes or amps. R represents resistance measured in ohms. The beauty of Ohm's law is that we can rearrange this formula to solve for any of the 3 variables. Here's a helpful triangle diagram that shows all 3 forms of the equation. Let's work through a practical example. Suppose we have a 12-volt battery connected to a 6-ohm resistor. We can use Ohm's law to calculate the current flowing through the circuit. Using the formula I equals V divided by R, we substitute our values. I equals 12 volts divided by 6 ohms, which equals 2 amperes. Now let's explore how resistance works in series circuits. In a series circuit, resistors are connected end to end, and the total resistance is simply the sum of all individual resistances. Parallel circuits are different. Here, resistors are connected side by side, providing multiple paths for current. The total resistance calculation is more complex. We use the reciprocal formula. Let's work through an example with 2 resistors in parallel. Suppose we have a 6-ohm resistor and a 3-ohm resistor connected in parallel. Using the parallel resistance formula, 1 over R total equals 1 over 6 plus 1 over 3. This gives us 1 over 6 plus 2 over 6, which equals 3 over 6 or 1 over 2. Therefore, R total equals 2 ohms. Now that we know the total resistance, we can use Ohm's law to find the total current. If we connect this parallel combination to a 12-volt source, the total current would be 12 volts divided by 2 ohms, which equals 6 amperes. Finally, let's briefly discuss power dissipation. Power is the rate at which electrical energy is converted to heat in resistors. We can calculate power using 3 equivalent formulas: P equals I times V, P equals I squared times R, or P equals V squared divided by R. Understanding power dissipation is crucial for circuit design, as it helps engineers select appropriate components and ensure circuits operate safely within their power ratings.